So allow me to introduce briefly the speaker of this session. So Dr. Elisabetta Carella, she's currently a researcher in CIEMAT in Madrid, Spain, former colleague of mine and a friend. And we're happy to hear from her what she has to tell us about R&D technology issues for a fusion reactor and the work she's been doing so far in CIEMAT. So Elisabetta, the floor is yours. Thank you.
Okay, thank you. This will be a really general speech about the technological issues that we have in fusion. It's not based on my work, but also in general lines on what we are doing here in CIEMAT. So, as you know, in fusion, there are two main actors that are the fuels, which are deuterium that we can easily find in seawater, and tritium. Tritium is not present in a natural way in our in our world. It comes from cosmic rays, but it is not easy to catch it. So we have to produce it. How? As you know, we are using lithium transmutation by neutron to produce tritium. There are two isotopes of lithium that can produce tritium, which are lithium-6 and lithium-7. We are mostly trying to use lithium-6, even if the isotopes of lithium that we can easily find in nature is lithium-7. So we have to enrich lithium with a lithium-6 isotope. So in general, we can see that in fusion, the primary fuels are not deuterium and tritium, but deuterium and lithium, because without lithium, we cannot produce tritium. If we have a look to a fusion reactor, we have the main actors that you already know, that are the magnets, all the diagnostics for the plasma, the heating systems, the vacuum system, the cooling system, that all works for a good power supply, the safety, to control the safety of the reactor, and there is an important work on the remote handling of all these parts of the reactor, mostly for the work that we have to do for the control of the plasma and the replacement of the fuel. The fuel is contained in a part called breather blanket that is located just behind the first wall. And it is the part in which I am working since I start with the fusion, since 14 years. So in the breather blanket, which is the role of the tritium blanket, of the breather blanket, mainly to convert the neutron energy, providing the 18% of the fusion energy in heat, and collect it by means of a high-grade coolant to reach high conversion efficiency and make fusion reliable energy. Produce all the tritium required as a fuel for DT reactors in the core, in the lithium-based breathing blanket, and fully recover it using, for instance, helium purge gas for continuous reinjection in the plasma, and reach so in this way the required tritium for sufficiency. Furthermore, it is important its role to contribute as a shielding for the superconductive coils. So it is important to assure a material's resistance to neutron and radiation damage. There is a bootstrap problem with fusion materials, that is that we cannot properly test components and materials without a fusion neutron source, because the neutron source that we can find in fission, for example, are not so powerful as the neutrons of fusion plants. We cannot build a fusion neutron source without component and materials. So we are trying to make some testing on a small scale, for example, with the important testing facility of IFMIF Dones that will be built in the south of Spain in Granada, and is already being built in Japan in the case of IFMIF. And maybe we have to assume that fusion power plant technology will remain at lab scale until demo and ITER will run. ITER will be a unique opportunity to test components and all the TBM mockups in demo relevant conditions in order to demonstrate that tritium breeding self-sufficiency can be achieved in a fusion reactor. What is TBM? It's a tritium breeding module that will be present in ITER, in the ITER program. And there are a lot of tritium breeding models that have been proposed from all the scientific community that is involved in ITER project. And the idea is to try to observe all these different proposals with the aim of being able to choose the better one for demo. So the proposal that came from EU, Japan, China, India, or US involve different kind of breeder materials that can be of solid type with ceramics, with lithium breeding ceramics based on titanium and on lithium, or with a liquid breeder materials based on lead lithium. The coolant can variate, can be helium or water, or in the case of one design that is currently being studied in CIEMAT and in US is the dual coolant lithium lead. In this design, the concept use helium coolant, lead lithium as a breeder, and also as the tritium neutron multiplier and coolant itself. So if we have a look to the two designs that have been selected for from Europe, there is the helium cooled pebble bed, which used ceramics based on lithium that are being currently produced from KIT. The structural material is Eurofer, and the neutron multiplier is beryllium in hexagonal rods, as you can see here in this.
Elisabetta, I think we are still seeing your ITER slide.
Oops.
Yeah, now it's moved.
Sorry.
Ah, it's okay. Here we go. Yeah.
Sorry, so you cannot see neither this one from of all the TBMs proposed by Europe. So speaking of HCPV, we have the neutron multiplier in hexagonal shape containing the breeder ceramics. The coolant is helium at a really high pressure. The first wall, the plasma protection, is a layer of tungsten. And the tritium extraction will occur with helium purge gas with a small content of hydrogen that can catch tritium produced inside the lithium ceramics. So the second TBM proposed by Europe is based on lithium and cooled by water. So the idea of Europe is to test the two technologies, the two kinds of coolant that are proposed in all the world, that are helium and water, and the two different kinds of breeder that are ceramics, lithium ceramics, and lead lithium. In the WCLL, we have water as coolant. The first wall protecting the plasma from the plasma is always tungsten. The structural material is always Eurofer, but in the case of breeder and neutron multiplier, we will use lead lithium. with an enrichment in lithium-6 for the reason that I explained in the first slide, that we need a higher content of this isotope of lithium to produce an exothermical transmutation reaction. In the case of this TBM design, it's really important also the tritium extraction from the recirculating lead lithium. It will not be used a helium purge gas, but we need to purify the lead lithium carrying the tritium produced inside it. So the present status of the technologies of this lead lithium has some really important issues, technologies, because it's not so easy to work with a liquid metal. The first important issue is the extraction of tritium from this lead lithium. Actually, there are several systems under selection for tritium extraction. We do not have the candidate, but we are still studying this kind of extraction system based on different physical processes. In one case, we have a permeation against vacuum. In the other case, we use a gas-liquid contactor. And in the last case, we have a liquid vacuum contactor. Then we have to solve the big problem of corrosion, because lithium is highly corrosive, and we have lithium moving in all the channels containing lead lithium in form of liquid metal. Then we have to purify also the lead lithium from all the solid activation and corrosion products that will be produced inside the breather tubes. And related to the movement of this lead lithium that is a metal, we have a problem of magneto-hydrodynamic with the coils, because this is a metal, so its movement can produce some recirculation of current and an additional magnetodynamic effects on this lithium, this liquid metal moving inside the wall breather blanket, a part of some important pressure drops. For example, having a look to one important problem with materials, that is the corrosion, we can see that the corrosion of related to lead lithium brings some important problems. Why? Because we have the deterioration of the mechanical integrity of the blanket structure due to the wall thinning, due to corrosion, the transport of the corrosion products that can be carried out from the liquid metal loop and can be also activated by the neutron present inside the breather. We have the formation of some precipitate. Their stagnation in the cold part of the lead lithium leads to safety problems. So this is there is an important impact on the operation of the wall system. And finally, there is the importance of a higher tritium permeation from the breather part to the coolant part. So there is an important, as you can see, from a material problem that is corrosion, we have a secondary really important issue related to safety, which is the challenge of fusion materials. Is really important because, as you can see, there are several problems that can be provocated by a simply corrosion effect. And if we have a look to the wall material present in a reactor, we have to take to try to focus our attention not only on the structural material that are the base of a fusion reactor, because without that a good structural material, we cannot build a fusion reactor, but we have also to take into account the functional materials that if lose their functionality, we cannot have a really good functioning of the reactor. For example, in a case of a solid tritium breeder or a liquid tritium breeder, if the blanket doesn't function correctly, no fuel to achieve the fusion reaction. So we do not have enough energy production. For this reason, it's really important to pay attention to all the materials present in a fusion reactor and study their effect with neutron irradiation. For this reason, it's really important to validate all the materials that we are studying in a big machine like ITER, because in this way we can be sure that they can be a good candidate for the first demo reactor. If we have a look to neutron and plasma fluxes into the blanket first wall and to the blanket, we can see that even if ITER is a really important experiment, we do not have in ITER the same, we will not have the same neutron fluence that we will have in demo. For example, in the case of ITER, we will reach only 3 dPa over its full plant life, only 1 dPa on a given TBM. In the case of demo or the next step generation of reactors, we may reach 18 dPa. Few designs have identified damage targets with facility programs. So in the case of ITER, we will have an important machine that will give us a lot of answers to the materials, but we will have a really lower neutron fluence. So again, the deal for our material is really big. Speaking about the transition from ITER to demo, you can see in this graph which are the present plasma discharge in the machines that we have already in Europe, and not only in Europe. And as you can see, there is an important difference from in days for year, for example, from ITER to demo. In ITER, we will have a plasma for less than 20 days for years, about 5%. And in the case of demo facility, we have plasma discharge times ranging from 2 hours to 2 weeks or more. So the plasma on time totals per year target will be about 30–50%. Are we ready for fusion? So it's difficult to have a question, to have an answer in this moment. We have a baseline material that are on more advanced than others, like structural materials or plasma facing materials. We have others that still need a lot of work. We need also the capability to scale up these new materials, so to be able to manufacture these materials that we are studying on lab in a big industrial facility. So we need more work to understand their variability with neutrons, with high temperature, and also the corrosion effect in a simultaneous way. So coming back to the issues of tritium breeding materials, we can ask some questions. No? Can our blanket design provide large TBR to guarantee a sufficient margin for success? Are we accounting for all penetrations, materials, non-homogeneity, radiation, and corrosion? Which is our level of confidence from validation experiments? Can we recover the tritium from fluids with high efficiency? and we find tritium permeation barriers that actually work in their service environments with corrosion, with neutrons in core and ex-core? Can we maintain losses throughout the breeding zone? Fluids pipe, material trapping, plasma fueling, leakage to secondary, hot cells, where losses are, or the loss to environment. So are we able to consider all these losses and still be able to speak of green energy? Which are the technical future of our future power plant? Reliability, as far as possible, we need to have a modular components made in factories and designed for manufacture. A continuous operation is the key. Reliability of system and whole plant diagnostic is vital. Establish industry involvement and supply chains. Material data is a crucial point. Improve all basic material performances and bulk manufacturing tolerance, considering impurities and size, manufacturing and joining techniques at industrial scale. And finally, accelerate the development to be a real clean energy option. In this graph, you can see the total mineral demand for clean energy technology for the scenario of next year. And as you can see, in this moment, fusion energy is not present. We have a scenario with a really big increase of energy demand. So we need to be faster if we want to be a really option and a really alternative to fossil fuels. So concluding, tritium self-sufficiency is a really critical point to demonstrate fusion energy. Basically, ITER TBM program objectives consist of learning from the design and operation of the tritium breeding systems, how a demo breeder blanket have to be designed and operate for demonstrate tritium breeding capabilities of a given design. The successful outcome of the TBM program is therefore essential for designing, manufacturing, and operating a demo plant. A lot of R&D is still needed in the frame of materials and technologies to assure that fusion could represent a real alternative fossil fuel in the future of our world. A good scientific community able to work in group and collaborate as much as possible will help to achieve this goal faster. And of course, all your work and interests are welcome to contribute to this big issue that we have in this community. Thank you.
Thank you very much, Elisabetta, for this very comprehensive and interesting talk, especially in the field of materials for fusion, which I think it's a really relevant part of fusion research at the moment, since like you mentioned, we are moving towards the big facilities. ITER is under construction. Well, it's under assembling now. And then all of the research now is for materials, at least, is also focused on demo reactor, and there are different requirements among the two. So it's a really interesting field to be at the moment, with a lot of challenges, as you mentioned, because you focus, for example, on the tritium breeding, and but also all the issues and challenges that come with the dealing with tritium for fuel for the future machines. So of course, we always rely on a we call it almost endless supply of fuel, but then we have to be able to deal with that fuel once in the fusion machine. So thank you very much for this, and also for mentioning that this is something that requires the interest of students at the moment, and on what was going to be future researchers. And also, I would like to point out to the audience that also FusionNet supports projects and thesis, like master thesis projects, also in the institutions that are doing research for fusion. Not only companies, not only, like you saw in the previous talk, we have also companies that we support, but also we are part of the Eurofusion network. And then there is the possibility for students to be able to join these projects at the institution. So also for CIEMAT, I know there is the possibility to work also for your department, the materials, technology of materials in CIEMAT. So thank you very much. I think I will open the floor for questions. And
You're welcome. Sorry for the presentation, because maybe you have not seen some slides.
Just a couple of them, but it was okay. So yeah, it was okay. So yeah, I'll leave the floor to questions. So I'll read they're available in the chat, but I will read them for you.
Okay.
So
any master's project with university? Yeah.
Mhm.
FusionNet Master is in collaboration with the Carlos III University of Madrid, I think so, no? Dario?
Yes, that is the European Master, the Fusion EP Master. That's from the Erasmus Mundus scheme. So also supported partly by us, but yeah.
A part of it, there are some master from Spain universities like Autónoma University of Madrid, and some other from maybe Politecnica that are related to nuclear energy and energies in general. And we do not organize a master in CIEMAT because we are not a university, but any master student can come here to make some work practice or the DFM if you are interested in it. And we can offer PhD positions in CIEMAT. So if you are interested in it, we have once per year, we have a call for PhD students.
Yeah, thank you. So let me add to that, since yeah, of course it's easier to go to the projects in CIEMAT if you're from Spanish universities, but it doesn't mean that it excludes that if you are from a university outside of Spain, you can go to CIEMAT, and you can do that through FusionNet. So again, I will give more information on that later today at 2 p.m. But just to let you know that there is also the chance for you being enrolled in a master program in a university from Europe. Then it's possible for you to be able to carry out some research in CIEMAT. Of course, then you will be in contact with the local supervisor there in CIEMAT, and it has to be arranged with your university, but also you can receive FusionNet funding for doing that internship or master project. So aside of the opportunities that already exist. Okay, and I am reading that there is a person from Spain that is interested in it. I think that if you write to Dario, he can provide you the contacts with FusionNet person here, or my contact, or the one that you need. No, Dario? Yes, of course. Always happy to connect and to send people to CIEMAT, institution close to my heart, but also to their universities. Okay. So there is also a question that will the slides be available, Elisabetta? I think that's fine for you. Yeah. Okay. So yeah, we will record. This session is being recorded, so as yours. So we will put these sessions later on our channel, so you will have access to these slides. So yeah, and also please feel free to contact me and and Elisabetta. But yeah, we'll always happy to share the network, and that's the main idea of this. So perhaps while I wait for somebody else to think of a question, I would like to make one of my own, because since we are mentioning that this is in general, fusion is a research topic that is going to be handed to the next generation and so on. So this is and this is valid for all the fields like plasma, modeling, but also materials. So what do you think in your field, what would you think would be the challenges that will be left for the next generation of fusion researchers to solve? Because you are currently tackling some of them, and we are confident that this will be solved according to the European fusion roadmap. But then what do you think will be the challenges that the next generation has to focus on your field? A lot. Yeah, the problem is that fusion is really complicated with material, so it's really hard to find a really good candidate, and we are constantly fighting with all the problems that we have in a fusion reactor, that are neutrons, irradiation. So I think that we can try to solve some problems on R&D point of view inside the reactor, but then there are all the technologies that have to be developed in the part that is outside the core,
not only the core, the reactor. For example, the tritium extraction system that I was speaking about that is really important, is crucial to have a good tritium extraction system, because if you do not have it, you will not have tritium inside the fuel. And in this moment, we are really centered in solving the problems inside the reactor, that we are not having a big look to all the technologies that have to be developed outside it. So I think that there is a big work regarding all this technology, all the loop outside the reactor, the pump that we will need a pump that are not still in commerce. We will need a helium at 8 megapascals. So, for example, for the coolant of HCPB, we will need something that is still not designed. So, apart of all the issues that we are working on related to the core and the reactor itself, there will be a lot of work of for all the integrated facility. I think that the name is integrated, the tritium fuel cycle outside the reactor. And I think that there is always time to improve all the work already done, because it's like a living energy. And it's not maybe the term, but I mean, it's something that can change always. If we find a new material that can be used for or is really good for solar energy, and suddenly can be used also in fusion, we will check it and try to use also in this new energy. No, I mean, nothing is closed in this moment. We are trying to close chapters because we need to build a demonstration reactor. But in this moment, everything is open. Actually, in ITER, we are going to select materials, because as you can imagine, in all the world, there are so many candidates that have been selected that we need to start with the checking of the really good ones and the not so good ones.
Yeah, that's really true. It's a step-up process. So now that you mentioned corrosion being a big issue, I remember that there is also an experiment in CIEMAT built with a liquid metal. Can you please tell a little bit more on this, because this is something, a facility that I suppose you will also need researchers for this.
Yes, always. Yes. Actually, we have a liquid metal laboratory, and there are two big experiments. There are two loops, one related to the tritium extraction system with the PAV facility, permeation against vacuum, that you can see in this slide, and the other related to corrosion in dynamic conditions, because up to now, a lot of facilities that have worked with lead lithium have worked with lithium in stagnant conditions. Because if we come back to the TBMs, the liquid, if you look at the liquid breather materials, there are two main candidates. The WCLL work with the lithium that moves really slowly. So for this reason, and also because it is quite difficult to have a loop working with lead lithium in dynamic conditions, the big quantity of experiments and are not so much in Europe that works with the lead lithium are based on lithium in stagnant conditions. There was one in KIT, but it has been it stopped with this time life, because, as you can imagine, lead lithium is really corrosive, and the experiments have a lifetime really short. And for this reason, we have built a new facility in CIEMAT to supply materials and experiment to all the Eurovision colleagues wants to check their materials in dynamic condition with a really extreme condition, because in theory our loops work for DCLL conditions that work at higher temperature and higher velocities. So we need a facility able to work with these extreme conditions and check the corrosion, because faster the lithium, faster the corrosion is faster the corrosion. So we have to be able to observe how many time we can use our materials in this concept, no?
So I think this is then a dedicated facility where you would appreciate the support of students. Probably you would like to have an internship there, or a master thesis project, I suppose, for master students. Am I correct?
Yes. Actually, you are working now with the corrosion on coatings, because an important issue in fusion is that all the tritium produced can remain inside the breather blanket, because if you start having tritium in the structural materials, in the coolant materials, you will lose fuel and you will contaminate other ambients, no, other materials and other parts of the reactor. And for this reason, in Europe, we are using a coating that cover the structural material, the Eurofer, and it works as an anti-permeation barrier. But it also has to be an anti-corrosion barrier, because it works in contact with the lead lithium. And in CIEMAT, we have an important line on this, working on old and new coatings, in collaboration with ENEA and KIT.
Very good. Then, yeah, I think that's a good summary, and also good motivation for students to contact us and you and see what's going on. So I see one question here. That we're almost reaching the end of the session. So, do liquid breathers have greater tritium breathing capabilities than solid ones?
Yes. Actually, the TBR, the tritium breathing ratio, that is the tritium produced mainly the efficiency that has a breather blanket compared to the tritium that is producing is higher in the case of liquid breather than in the case of solid breather. Why? Because in the case of solid, you have a really localized production of tritium inside the ceramic, but the problem that has the solid breathers is that it is not so easy to extract the tritium from the solid breather. So you have a good quantity of tritium produced inside the ceramics, but then it's not so easy to take it to purge it with the purge gas. And for this reason, the TBR of breather ceramics is a little bit lower. At the same time, in the case of lithium ceramics, there is a lower permeation from the breather part to the coolant. And in the case of liquid breather, there is a higher permeation to the coolant. So you are producing more, but at the same time, you have a higher permeation also. So there are pros and contrasts in both designs.
Well, thank you very much, Elisabetta. I think with this we can conclude the session. Thank you also for the speakers to be here. Thanks a lot. It was really, really interesting. And